Hello everyone, this is lesson 5.2 on the perpendicular bisectors, and the last lesson you learned about midsegments. Now midsegments were segments in a triangle that intersect at the triangle's sides midpoints, and you found out that there were 3 midsegments in a triangle. Each midsegment is half of the length of the opposite side and also parallel to the opposite side. So with perpendicular bisectors, and I don't know if I can write this down here, probably not. We'll come back to this page. But go ahead and title your notes 5.2 Perpendicular Bisectors. And a perpendicular bisector is just like what it sounds. It's a line or line segment that passes through the midpoint, since it's a bisector, of a side of a triangle and is perpendicular to, just use the perpendicular symbol, to that side. Okay, so here we can see that point P passes through the midpoint of segment AB because it says that those two markings are congruent and shows a right angle symbol, so CP, line CP would be a perpendicular bisector. All right, so we'll come back to this page. In a triangle, the perpendicular bisectors, the point where all 3 of the perpendicular bisectors meet for each side of the triangle, is called the circumcenter. So we're going to do a little discovery here of the circumcenter. So go ahead and write this down too. The circumcenter is the point of concurrency of the 3 perpendicular bisectors. Okay, make sure you write that down. A point of concurrency is just where the points meet. So where 2 or more lines or segments meet. So with the midsegments, the midsegments did not ever intersect each other. Okay, they only kind of touched each other at the midpoints. But with the circumcenter, it's the point where the perpendicular bisectors meet each other. So for number 1, triangle XYZ is shown below. And then, actually, I think I'm on the wrong page here. Oh, yes. All right. Sorry about that. Okay, so recall, well, that was still a good note to take. But anyways, recall that 3 or more lines are said to be concurrent if and only if they intersect at exactly 1 point. And then triangles' perpendicular bisectors are concurrent. Their point of concurrency is called the circumcenter of the triangle. Okay, just like what we mentioned in the other link. Uh-oh. All right. Sorry, my computer's kind of wigging out here. All right. In the applet below, point C is the circumcenter of the triangle. So here, you've got just a regular acute triangle, and the dotted lines are the perpendicular bisector, and this would be your point of concurrency. In other words, the circumcenter. All right, so perpendicular bisectors meet at the circumcenter in the triangle. All right, so a couple things to note here after you've written this down. Please go ahead and make sure you draw a triangle in your notes, draw perpendicular bisectors for them, maybe use a ruler, okay, when you're making this, or a protractor, and then note the point of concurrency, the circumcenter. Okay, make sure you're including all of this and labeling, taking good notes, okay? So is it ever possible for a triangle circumcenter to lie outside of the triangle? I'm just reading question 1 below. So would it be possible for point C to be outside of the triangle? What do you think? If so, under what circumstances? Oh, goodness. So let's kind of move this around here. So as you can see, kind of the more obtuse I make this, the larger I make this angle, the closer the point of concurrency gets to this line here. What if we made it a right triangle, 90 degrees? Where is the circumcenter? The circumcenter is on the hypotenuse, the midpoint of the hypotenuse. All right, so for a right triangle, actually, let's start with acute. For an acute triangle, the circumcenter is inside. For a right triangle, the circumcenter is on the hypotenuse. And what do you expect it would be if it were an obtuse triangle? It's going to lie outside of the triangle. So for obtuse, the circumcenter will lie outside of the triangle. Right, so those are also things you should take note, all the properties of the circumcenter. And then we answered number 2. Is it possible for a triangle circumcenter to lie on the triangle itself? Yes, that would be for a right triangle. If your answer is yes, where on the triangle is this point C lie? It will lie on the midpoint. Of course, since it's, well, when it was a right triangle, it lied on the midpoint. Okay, and then construct a circle C centered at C. Construct a circle centered at C that passes through J. What do you notice? So what we're going to do, go back to the original triangle, we're going to construct a circle centered at C and that passes through point J. So I'm going to start it at C and drag it out to point J. So what do you notice if we construct a circle that has a center at the circumcenter and passes through one of the vertices of the triangle? Well, it passes through all 3 of the vertices of the triangle. So that's another thing here to notice. This would be called a circumscribed circle. Circumscribed circle is a circle that center is the circumcenter, and passes through the vertices of the triangle. Passes through vertices of triangle. In other words, the vertices of the triangle lie on the outside of the circumscribed circle. So this is a circumscribed circle. Okay, so back down to here, what do you notice? So you would say right here that the circumscribed circle passes through each vertex of the triangle. Okay, so then let's generalize. The circumcenter of the triangle is the only point the circumcenter of the triangle is the only point and we're going to say, if you need a hint to complete this up, consider the lengths of CK, CL, and CJ. So what's the relationship between the points CJ that one and that one? So those are the 3 segments they were talking about. They are all congruent. They're not angle bisectors, so don't get confused with that. But the thing to note here, and I'm going to clear this off so I can write some more, is that the circumcenter is equidistant to the vertices of the triangle. Okay, that's another key thing to note here. So the circumcenter is equidistant to the vertices of the triangle. All right, so lots of things to note here. Please make sure you have all of those key things about the circumcenter and the circumscribed circle written down, and you have this diagram in your notes. Now we're going to just take a quick look at and apply this to perpendicular bisectors and other examples. So back to the kind of the notes from the smartboard here. So we've got a perpendicular bisector And back to this point. A point is equidistant from two figures if it is the same distance from each other. Okay, so that's what equidistant means. It's just the same distance. So here, what we said is that the circumcenter is equidistant from the vertices of the triangle. The same thing kind of happens with when you have the perpendicular bisector. So this point C here is equidistant from the endpoints of the segment that it bisects. So here, if we drew in a segment AC and AB, then those would be congruent. If we made another point on line CB, say we made a point here and called it point D. And then if we drew segments AD and BD, those would also be congruent, right? Because it's equidistant from the points that it bisects. Right, and then we kind of went through this already. Perpendicular bisector theorem. Oops. I'm just pressing all sorts of buttons and I don't mean to. Any point on the perpendicular bisector of a segment is equidistant. Oh boy, here. Okay, equidistant from the endpoints of the segment. So that's just what I was saying. Sorry about this, guys. AC and BC are congruent. If you picked any other point here, say you picked a point down here and called it X, BX and AX would be congruent, right? So here's an example for you. It says that Cn equals 3x minus 10. So here you have, how do you know what point C is? Well, you see how the triangle, you've got a triangle and you've got the perpendicular bisectors. So you see the three perpendicular bisectors here that are marked at the right angle, and you have a circle that is circumscribed around the triangle. So this circle is circumscribed around triangle PNK, which implies that this little thing kind of implies or therefore this little double arrow symbol, that C is the circumcenter. Also, you have perpendicular bisectors. So if you have perpendicular bisectors and they all meet at point C, then that's another reason why C would be the circumcenter. So here it says that Cn, and notice that Cn is not drawn in, but if we drew it here, Cn and CK and CP, we know that one of the properties of the circumcenter is that it's equidistant from the vertices of the triangle. Therefore, they would all be congruent. So CP, Cn, and CK are equal to each other, their lengths. So that means that we can just take these two equations, set them equal to each other. So let's do x squared minus 20 equals 3x minus 10. And this problem involves factoring. So let's move everything over to one side of the equation. Minus 3x plus 10 is minus 10. And if we were to factor this, we would put x in the first position, and what multiplies to 10 but adds to negative 3? That would be, what, negative 5 and positive 2? Oops, oh goodness. So then our equation here our answers would be x equals 5, x equals negative 2. But it asks define the distance of CP. So we'll just take both of our values and plug them into 3x minus 10. So if we did 3 times 5 minus 10, we would get 15 minus 10 would be 5. And let's check negative 2. So if we did 3 times negative 2 minus 10, we're going to get a negative number here. So negative 2, it has to be ruled out. So CP would be equal to 5. All right. So a few other little things here that we could do. KM is perpendicular bisector of JL. So here, KM is perpendicular bisector of JL. And since M is on the perpendicular bisector, it is equidistant from J and L by the perpendicular bisector theorem. Therefore, those two are congruent. So we can set these two guys equal to each other. Okay, and then also, if K is a perpendicular bisector, then these two segments would be congruent. So we could set 5y equal to 2y plus 9. All right, I will let you solve that simple algebraic equation by yourself. You should get x equals 4, y equals 3, and if you plug them back in to get JK and ML, you would get 15 and 28. Right? I don't think it's necessary to go through all of that. Okay, so let's talk real quick about the perpendicular bisector converse. I know this video is a little bit longer than normal, but this is a tricky concept, so we want to make sure that we get it thoroughly explained. So the converse would be that any point that is equidistant from the endpoints of the segment is on the perpendicular bisector. So the regular version said that if you've got a perpendicular bisector, any point along that perpendicular bisector is equidistant from the endpoints. This says that if any point is equidistant, so say point D here, if D is equidistant from A and B, so the same distance, then it must lie on this perpendicular bisector. So we know that CP is a perpendicular bisector to AP, but we don't know that D is on this line unless we know that these two markings are congruent. So we would then know, confirmed, that D is in fact on that perpendicular bisector. So here, let's look at this one. So DC is a perpendicular bisector of AB. Okay, so we know that those two are congruent. And then we know that AE and BE are congruent. So if we know that E is equidistant from the endpoints of this perpendicular bisector, then we know that it's equidistant. And it lies on the perpendicular bisector. For this one, PQ is the perpendicular bisector of RS. So I guess the question here is T on the perpendicular bisector? Here we would say no, because it's not equidistant from the endpoints, because this is 14 and that's 15. If they were both 15 or both 14, then it would work, but here it's not. So this would be T is not on the perpendicular bisector. All right. So that concludes this lesson. You will do more examples in the notes, or not in the notes, sorry, in the Edge Elastic assignment. All right, I hope you guys have a great weekend, and I will see you on Monday.